classical reality is the robust form of reality, and it has this characteristic feature that I can ask the state, I can say, hello state, what is your state of reality? And it comes back to me and I says, oh, my state is I can have a body like this object here, and I can ask it what its shape is, and it says I've got a round thing at the end and a round thing in the middle, and like more or less cylindrical and things like that. Now, quantum reality, you can't do that. What you can do is if you have an idea what the state is, a pretty good idea, and you can say, is your state X? You think it should be X by now, and you ask it whether it's X. And if you've got it right, then it will say, yes, you got it right with certainty. This is Einstein's, what I'm calling Einstein's dictum. He introduced this idea of what I'm calling quantum reality. And you can see what I'm saying here. It's more or less what I was saying there. That if you can ask the system with certainty and without disturbing the state, so if you know what the state ought to evolve to, then you can say, is your state, as I think it ought to be by now, evolving the Schrödinger equation? And the thing will say, yes, you got it right, with certainty. And that gives it a kind of reality. However, it is a different kind of reality. And the key thing to this is that it is a different kind of reality. Let me give you an example of quantum reality. This is a very simple example. This is a spin-half particle. And the notion of spin for a spin-half particle is very beautiful in quantum mechanics, because you can think of it as behaving like a little sphere spinning around an axis. The amount of the spin is always the same, but the direction of the spin about that axis could be different. You've got all these different possible states. Now, I'm supposing the state is, as indicated in this picture, up and to the right a bit. Then that is a linear combination, a quantum combination of up and down. So you might usually talk about up and down as the two basic states. Up and down means right-handed about the upward direction or right-handed about the downward direction. And then any other state is this quantum complex combination. Well, I've got W and Z instead of alpha and beta, but that's the same thing. W times up plus Z times down will produce all the possible different directions. And I always regard this extremely beautiful because it ties in these complex amplitudes of quantum mechanics, which seem very abstract things, with something very concrete, namely this direction in space. And the direction in space is tied up with this quantum notion of superposition of these different directions of possible spin, and it ties it up with the directions in space, which I always regard as an extremely elegant and beautiful feature of quantum mechanics. Now, you see, here is an example of quantum reality, because if you've done some experiments and it's put it into the state pointing in the direction we have in the picture, up and to the right, then you can make a measurement on it in that direction, and it says, yes, you got it right with certainty. I can do it 100 times. Every single time it says, yes, you got it right. If I tried up or down, then it would say sometimes yes, sometimes no. These probabilities being given by the squared modulus of the W and the Z, and the ratio of the two, which will give you the probability. So when you don't get probability, that means you got it right. When you haven't got it quite right, you'll get probabilities. And if it's almost right, you'll get almost certainty for your probabilities. So that's the way it works. Okay. Now, this is quantum reality. Now, it's curious, but as far as I can make out, they both make a consistent picture. Now, I have here a pretty severe test for the picture. This is an example of an Einstein-Podolsky-Rosen situation. Time is going up the picture as before, and you might slice it in different ways, have different observers looking at the situation. But the real observers in the picture here are Alice and Bob, for some reason. Well, they're A and B, I suppose. So Alice and Bob are considered to be these two observers. They each take away from the initial state. Imagine their states are represented by the black lines going up. Alice goes up to the left and Bob is up to the right. They start off together, and each of them they're presented with a box which contains a particle of spin 0, so it has no direction attached to it. Then this is split into two spin-half particles, and Alice is given one of them in this closed box. Bob is given the other one, and they go away to a long distance apart, maybe light years apart, even if you like, or they could be different planets, a long way away. and then they settle down. And so that's the picture. You can see them separating, and then they settle down. And then one of them, let's say Alice, has a look and makes a measurement in a certain direction. In this case, the measurement direction, I think, is up and to the right. You can see that little arrow. Her measurement is the top point on Alice's line, and she's making the measurement, and she finds the answer, no, it's not that direction, it's the other way. Now, Bob, later on, and his measurement point is somewhere further up on his line, and he makes a measurement, and there are certain rules which prevent Alice from sending signals faster than light. The crucial thing about this is that you can't send signals faster than light. And does it make sense? Well, it does. But what is the quantum reality? It's very strange. The quantum reality, as you can fiddle around and see what it must be by looking at observers moving with different speeds and so on, must travel back on the past cone. So it looks sort of retroactive. Alice has made her measurement, and she's seen that it's not in the direction she chose, which was up to the right. It's therefore turns out to be the opposite direction, because that's the only possibility, is yes or no on a spin half particle. Either yes or no, and it says, nope, you got it wrong. And so this information travels backwards along the past light cone. So you see these sloping lines away from her point, right on the top point on the left-hand branch. The sloping lines are the past light cone of Alice's past light cone. And when it hits Bob's world line, that is the quantum reality of his particle. So the quantum reality has become the opposite of what Alice's one is. But since Bob can't say, hello, state, what is your state? That's not allowed. It's only quantum reality. All he can do is try different possibilities and see what the answer is. Very strange picture, but it does seem to be completely consistent. So the quantum reality goes backwards in time. Bob makes a measurement. He can't use this information to send a signal faster than light because that's not the way quantum reality works. The way quantum reality works is that if he had chosen the right answer, which would have been opposite to Alice's, well, I guess the same direction as Alice, then he would have got the answer, yes, you got it right. But he has no way of telling that without Alice sending a signal to him, and that would be slower than the speed of light, and so she can't do that. So although the quantum reality has become a kind of reality for Bob, it's not something that he can do anything with apart from you make a probabilistic measurement. And then he makes it later on, and then his quantum reality goes back and hits Alice's world line before she's made her measurement. So when you know the full answer in the picture, sort of godlike, you look at the whole picture and you see what the results were they made. You can then work out what the quantum reality must have been. But there was no way that either one of them could have determined what this quantum reality is. So it seems to be a consistent picture, a peculiar one, but nevertheless, that's the picture. Okay, now in this picture, I have a sort of combination of quantum and classical reality in the sort of way I understand it. At the bottom, I imagine a laser which is sending a high-energy photon to a beam splitter, or half-silvered mirror, if you like. So this photon is split into going horizontally and going vertically. Vertically downwards, so you won't worry about it, it just goes down. If it goes vertically horizontally, then it hits this lump of material, and considering it's a pretty energetic photon, so it hits it and starts to move it. But since the photon is in a superposition of being horizontal and going down, the impact on this body will be a superposition. Now, as you move your way up the picture, and you can see the classical reality is determined by the curvature of the space-time is produced by that body as it's put into a superposition of two locations. And this goes up until the Dioschi time, if you like, is when the collapse is supposed to take place. And if you like, that's sort of where consciousness comes into the picture. It retroactively, since it went the other way in this picture, it retroactively goes back to the classical reality is what the classical space-time does, and you have to say, well, the classical reality of that space-time goes right back to where the thing started to bifurcate. And so the classical reality you see with this marked at the left-hand side upper part of the picture, and the quantum reality sort of encompasses both until the collapse takes place. And somehow the quantum experience has to do with the branching of the two. Now, there's always been a problem, I think, as Stuart emphasized in his talk, about things seeming to happen too fast. And here I have a picture, it's rather crudely drawn, of somebody playing tennis and has deciding at the last minute whether to hit it right or left. And according to conventional neurophysiology, it's too late to make a conscious decision because it has to be done much too fast for the nerve signals to take place. Nevertheless, the conscious Roger Federer or somebody down there who's decided to hit the ball one way or the other, and that choice, according to him, was made consciously. Now, according to conventional neurophysiology, that can't be because there isn't time. But I'm trying to argue that no, that consciousness could be, as long as it has this retroactive aspect. It somehow feels out what's happening in the future and retroactively goes back. So it's got to be as though somehow the two alternatives of going one way or the other are coded already in some kind of superposition. At what level and where, I'll leave it to Stuart to make a comment about that. But somehow these two alternatives are there, programmed in a certain sense in quantum superposition. And the choice can be made in this retroactive way to influence which choice actually is the one that's made. So that it could be a conscious decision, although it can't be understood in these terms. Now, this all ties in with these early, very remarkable experiments done by Benjamin Libet, which I did talk about in my book, The Emperor's New Mind, right at the end, and I gave a sort of explanation which is the one which I would believe now, strangely enough, although I didn't explore it at that time. What is this experiment? Well, you have somebody with an operation on the brain, which has nothing to do with the experiment. The experimenter was given permission to do this experiment while the patient had a brain revealed, I guess, and electrodes on the finger and the corresponding another electrode on that part of the sensory cortex, which will tell you where the feeling of the sensation will be registered in the brain. So you see this little mark at the top. I'm going to work my way down the picture. This little mark at the top is the stimulation of the finger. And you ask the patient, well, when did that happen? And there's a fast-moving clock on the wall. And the patient says it was at such and such a time, which is almost coincident with the actual time. And so the feeling of the stimulation of the finger is indicated just below the mark there. Now going to the second horizontal picture, and now we have a brain stimulation, and curiously enough, at up to half a second, nothing is felt. The bottom picture shows you more what happens. Up to about half a second, nothing is felt, and then after half a second, then it is felt. The brain stimulation is felt as though the finger had been stimulated, but not the same. The patient can distinguish the actual stimulation of the finger from the brain stimulation. But it does feel sort of as though the finger has been stimulated. It takes half a second, that long. Now, this is the very remarkable one. The next line, suppose the finger is first stimulated, then a quarter of a second later, the part of the brain is stimulated, and somehow nothing is felt about the actual stimulation of the finger. It's only the brain stimulation is felt half a second after that starts. Somehow, the feeling of the stimulation of the finger it's unfelt. And that's a real paradox, unless somehow the feeling is not actually felt until later, and then about the clock isn't seen, sort of registers as being later. So that's consistent with the top line. So both things do not happen until later, but somehow it's referred back as though it had been earlier. And so in the bottom line, you can see that if the brain stimulation is first, then it sort of makes sense again. I won't go into the details of that, But it does seem to me it would be very nice to have this experiment repeated. And I don't know, Stuart will explain why it hasn't been done again. I think it really important experiment that should be done. Some version of this experiment should be done again. And this wasn't before, it was still in the 1990s, I think, when this was done originally.